Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're going to look at some real-life differential equations. So in this video, we're going to explore how differential equations apply to the real-world scenarios and help us model and solve practical problems. We're going to focus a lot on exam questions in this video and specifically looking at scenarios where we talk about velocity, how it changes over time, acceleration as a rate of change of velocity, force as it relates to mass and acceleration, and power in relation to force and velocity. Work done by a variable force, such as stretching things Hooke's law, will also be covered. So just to be aware, this is really only suitable for higher level students, although the syllabus says that ordinary level students have to have an understanding of differential equations. You will not be required to do any actual differential equation solving. So if you've not already revised integration, I suggest that you do that first. In the description below, I've linked the integration techniques video. However, while we're going through, I am going to use this idea of a checklist with regards what type of integration we should do. So here's the easiest way to figure out what we should do. The first check is there a formula on page 26? If there is, use it. And we have a little caveat on that I'll talk about in the next slide. The next thing you'll always check is it a composite function? So it's really important that you understand what a composite function is, how to identify it, and if it is a composite function, we're going to work backwards. So this will be the kind of working backwards of the chain rule, and it's integration by substitution, or also known as U substitution. And then if neither of them work, finally, we would try integration by parts. Integration by parts tends to be the one students prefer over substitution. However, this can get very, very messy. So it's really important not to use it in a case where there is a better approach. There are scenarios where either integration by substitution or integration by parts in theory will work, but the integration by substitution gets very, very messy and gets into maths that you may not be able to do. So it's really important that we follow this checklist. So here are our rules of integration from page 26, and there are three bits in particular that I want to point out, and one that we see quite a lot, that is the basic chain rule in reverse. So if we have a composite function, if we have chain rule, we do have that idea of integration by substitution. However, there are some really basic examples that we don't want to waste our time doing integration by substitution. Instead, we want to work very quickly. And how we're going to do that is we're going to work backwards on the chain rule, which means we're going to integrate it as per the rule in the log tables as normal. And then we divide by the derivative of the inner function. So whatever the inner function is, we differentiate it and then we divide by it. Now, the main ones we're going to see are 1 over x. So what we want to use for that identification, it will look like something like this. So 1 over ax plus b. Two things to note about it. The top will be a constant, and that's important. It doesn't have to necessarily be 1. It could be 3, it could be 5, but it needs to be a constant. If there's an x up there, we're not dealing with this simple case. And the second thing is it's linear in the denominator. So what that really means is we are dealing with an x to the power of 1 in that bottom line. If it's x squared, if it's something else, it's going to be a different type of integration. This can be the trickiest one to identify, but it's one we see a huge amount, so it's really, really important. So we are looking for any version of 1 over ax plus b. The other two that we see are a little bit easier because we're more used to working with them in differentiation, and that is cos x and sin x. So things like cos 3x or sin 3x, we may have to work with those. When we're dealing with real life differential equations, we have some really important ideas that we will link back to. The first is the idea of velocity being the rate of change of displacement, so ds dt. The acceleration being dv dt, or another way to say that is v dv ds. Force is mass times acceleration, but as we've done in the line above, acceleration can be defined as dv dt or mv dv ds. So Either we're working with velocity and time or velocity and displacements. That's why we have two different versions of acceleration. If you're not familiar with these, I've also linked in the description below deriving our equations of motion using differential equations, and I go through how we get acceleration as v dv ds there. So another formula that's less common but could come up is power is equal to T times V, where T is attractive force. So it is a force that is pushing it forward. And the last one here is the idea of work done by a variable force. So most students know their formula for work as F times S, so force times displacement. However, if that force is variable, if that force is not remaining constant, and we think in terms of Hooke's law here, we have this integral. So the integral of the force written as a function of displacement dx. So we'll use that in the video and you'll get to see how it works. So these are important ones to make yourself aware of and make sure you are very comfortable with these formulas. So this is from the SEC sample higher level paper. It is question 3, part A. This is looking a little bit about deriving using calculus and expression for S. I go through these derivations in a lot more detail in the video linked in the description below. So a particle has initial displacement SO, so S0, from a fixed point P. It moves away from P with initial velocity U and constant acceleration A equals dv dt and d squared S dt squared. So we have two formulas here for acceleration. Use acceleration to derive an expression for S, the displacement of a particle from P at any time t. So a few things to note. We have a constant acceleration, meaning acceleration is a constant, and we can let that equal a. So let's start off with a, and we're going to use dv dt, just the first derivative, to get us going. Let's break this out. So we get a dt is equal to dv, and we're going to integrate both sides. So when we put our limits of integration here, when time is 0, our velocity is the initial velocity, which we use as label u. And when time is t, so at some point in the future, we have the final velocity, which we have the letter v for. So then on the left-hand side, we get at, and we're going to evaluate that between 0 and t. On the right-hand side, we get v, and that is evaluated between u and v, giving us at minus a times 0 is equal to v minus u. And then rearranging that, we're going to get v is equal to u plus at, which is a formula for the velocity at any time t. Now we were asked to derive an expression for s, the displacement of the particle, from P at any time t. So this question here is from the SEC sample higher level paper, and it is question 5, part B. So a rumour may be spread when a person who has heard the rumour interacts with a person who has not heard the rumour. Therefore, the rate of spread of a rumour within a group can be modelled as being proportional to the product of the number of people in the group who have heard the rumour and the number of people in the group who have not heard it. Okay, that's quite complicated. However, they have given us this differential equation and they have put it here. So if you can make sense of this, it is proportional. That's why we have the k to the product. So multiply the number of people in the group who have heard the rumour, so that's or, and the number of people in the group who have not heard it. So that's the total number, which is 1,200 students minus or. So we could be asked to make that in a scenario. However, here they've given that to us. So a student models the rate at which a certain rumour spreads. So anytime we're talking about rate, we're talking with respect to time unless they clarify otherwise. So that is d or, so the rate at which the number, so or remember is the number of people who know the rumour. So I have the number of people who know the rumour with respect to time, so d or dt. And that is equal to k or times 1200 minus or, where R of t is the number of students in the school who've heard the rumour at time t. One thing I would always kind of flag is the idea of what time is measured in, because depending on the question, it could be seconds, it could be minutes, it could be hours, it could be days, it could be years. So in this question, we're talking about days. On Monday morning, t equals 0, 100 students had heard the rumour. That's also going to be important, because when t is 0, or equals 100, and that's going to be something we're going to need as we solve this differential equation. So the question asks us to solve the differential equation to find an expression that relates or k and t. So anytime we solve, we're always looking for this up the top, so we're going to get or equals, and there will be a k and a t in our answer. So they give us a little note here. So note that 1 over y times x minus y is equal to 1 over x times 1 over y plus 1 over x minus y. So if they've given us this, it must be in somewhat relevant. It must help us in some way. So let's start with our first step. So when we're solving a differential equation, our first step is to separate. We want to separate the variables to both sides. So on the left-hand side, I'm going to bring this whole piece over. I'm going to leave the k where it is. So it's going to be or times 1200 minus or with respect to or is equal to k dt, because that k is just going to get complicated if we bring it over as well. So then we want to integrate, and when the time is 0, or is 100, and when time is t, we want to find an expression for or. So there are our limits. So now we're just straight into our integration. However, that thing on the left-hand side looks quite complicated. That's where we're going to start thinking about, okay, that note that they gave us, how can we use this to our advantage? Because if you take a look, that looks like a y and that looks like an x minus the y. So we can use that. So let's move over here to the side. So we have 1 over or times 1200 minus or, and that can be broken into 1 over x, where x is 1200, times 1 over y, where that is or, plus 1 over x minus y. Now what that effectively does is it's turned a product into a sum. And sums are much easier for us to integrate with, because if we have two terms, so two pieces added or subtracted, we can integrate each piece separately. So this has made our life so much easier. You can multiply in that 1200 if you like. You do not have to, and you can leave it out in front of the integral. So when we look here, we could end up with 1 over, I'm going to bring that 1200. The reason I can bring it out is it's a constant. It just has a number and it's multiplied by everything that's inside. So it's absolutely fine to bring it outside the integral to make life that little bit easier. Minus or. And that's all with respect to or. That's the left-hand side. The right-hand side here is going to be relatively straightforward, because it's just going to go kt, which we evaluate between 0 and t. So really our focus here is just on that left-hand side. So then when we want to start integrating that, we need to think about our checklist. So is there a formula on page 26? And the answer is yes. Both of those pieces are effectively a 1 over x. So if we think that's like a 1 over x, and that's like a 1 over effectively something like b minus x, but it is still both versions of 1 over x. So we're going to use 1 over x in the log tables to integrate that right-hand side. So I've put everything back here so we can see it properly. So this 1 over 1200 is just going to sit where it is. The first piece becomes the natural log of or. That's very straightforward. The next piece becomes plus the natural log of 1200 minus or. But then you have to divide by the derivative of the inner function, which means we're dividing it by a minus 1. And that's going to be evaluated between 100 and or. So effectively that's the same as minus minus ln 1200 minus or. This becomes kt, which we evaluate between 0 and t. I'm going to leave this 1200 out here for a minute. We get ln or minus ln 1200 minus or. And again, we're evaluating that between 100 and or. This is kt minus k times 0, so it's just kt. In order to make this a little bit easier, I'm going to actually multiply both sides by 1200 now. And bring that 1200 over here. So I get 1200 kt. And as well as evaluating, I can tidy this left-hand side up using our laws of log. So we're subtracting them. So that is ln or divided by 1200 minus or. So that's what we have. Let me just clean that up a bit. 1200 minus or. And then we're evaluating that between or and 100. So I'm subbing in, instead of or this time, I'm subbing in 100. Okay, so we're, again, remember, we're trying to get we're trying to get or on its own. We're trying to isolate that. Let's do a little bit of cleanup. So we have the natural log of or, 1200 minus or. And this becomes minus the natural log of 100 over 1100, which simplifies down to 1 over 11. Now, there's lots of different ways you can work with this. The natural log of 1 over 11 is kind of a nasty enough decimal, so you're welcome to put that decimal in. Don't round it too much. However, what I'm going to do is I'm going to use these laws of logs again. So I'm going to effectively divide this piece here, so the whole bit divided by 1 over 11. When we divide by a fraction, instead you multiply by its reciprocal. So this becomes the natural log of 11 or over 1200 minus or, and that's equal to 1200 kt. Now, what I like about that is the fact we're not left with any big nasty decimals. Now I can take e and the power of each side, e and natural log undo each other, which leaves us with 11 or over 1200 minus or is equal to e to the power of 1200 kt. We want to get that or on its own, so we're going to need to multiply out that fraction. So we get 1200 e to the power of 1200 kt minus or e 1200 kt. I'm going to bring all the or's to one side, so 11 or plus or e to the power of 1200 kt is equal to 1200 e to the power of 1200 kt. Pull out that or, gives me 11 plus e to the power of 1200 kt, and that equals 1200 e to the power of 1200 kt. So or on its own, bring it across that bracket, we're going to divide by it, 1200 e to the power of 1200 kt divided by 11 plus e to the power of 1200 kt. And that's our answer for or in terms of k and t. So part 2 of this question says, by Wednesday morning, 250 students had heard the rumour. So remember, Monday is T0, so that means Wednesday is T equals 2, and we know that or is equal to 250. Now, most students will go and take their final answer and plug that in. If you do, you have a good bit of work to do, because the fact that we're looking for k and k appears in 2 different parts. So if you want to work that through and sub that in, that's absolutely fine. However, if you want to save some time, and this exam can be very time consuming, it is nice to go back to the previous part and look for a time when k was kind of not isolated, because we won't have had it on its own, but it's only in a single term. So actually, if I go back to our previous part, we had a line that was ln 11 or over 1200 minus or is equal to 1200 kt. And that's a much better line for me to work with, because my substitution is going to be so much quicker. So when I plug this in, so 1200 minus 250, and that equals 1200 times 2 times k. So then to get my final answer, I'm going to do k is equal to the natural log of this simplifies down to 55 over 19. And then I'm going to divide that by 1200 by 2, which is 2400. And that gives me my answer for k. When you put this into the calculator, we get quite a small number. So we get 4.4287 by 10 to the power of minus 4, which is 0.00044287. Now, if you feel like that is too complicated to go back and find a different line, absolutely try it by subbing in the value of or and t into what we have, but it is a much longer calculation in that case, but you should get exactly the same answer. So if you have worked it the long way, or if you want to work it the long way, here are the steps needed to go from our final answer from part 1 to a value of k without backtracking to a previous step in part 1. So part 3 asks us to sketch the shape of a graph of or against t to show how the model predicts the spread of the rumour. So what we need to understand are values of or for each of those values of t. So you have a few different ways to do this. You can absolutely just go with your formula for or into your calculator and sub in values of t and change them. Another option is to use the table or function in your calculator. You can put it in terms of f of x and x, and it will give you everything you need. Here is the table that we get. I've put in 2, even though it's not marked as one of the days because we were given that information in the question. So we have at t equals 0, we have or equals 100, we were given that. T equals 2, or equals 250, we were also given that. And then we've calculated when t is 5, t is 10, 15, 20, 25, and 30. So if we plot these points, they're not going to be absolutely perfect, but we can see that from kind of t equals 15 onwards, we're pretty much up there at the 1200. So we get a graph that is roughly this shape. So this question is from the SEC sample higher level paper, and it is question 6. A learner driver is practicing driving around a roundabout. The motion of the car may be modelled as horizontal circular motion around centre O, with radius r and constant angular speed omega, as in the diagram above. Write an expression for S, the displacement of the car, relative to O at any time t in terms of or omega t, and your expression should use the unit vectors I and j. Note that t equals 0 when S is along the y-axis. So this feels like a very complicated question, but actually what they're asking is relatively straightforward. If we look at the diagram, they're basically asking, write this point in terms of I and j. Okay, that's literally all they're asking. This point in terms of I and j. Now, we know that to resolve anything, we can write it as the magnitude cos of the angle I plus the magnitude sine of the angle j. So that's our general formula. And the few bits we need are, well, what is the magnitude of our displacement? So because it's going in a circle, that is always going to be equal to the radius. That is its length. So that we're going to sub in for or. Now the angle. So what is this angle here? So let's think about that. So we have an angular speed, which is omega, which is radians per second. So then we want to understand, well, what is that in terms of an actual angle? So what we're going to do is we're going to multiply omega by time. So that is, if we think in terms of our dimensional analysis, that is radians per second times seconds, which gives us radians over seconds times seconds, which is literally radians. Now I know dimensional analysis, we don't put in our radians, but it's just to understand how we're getting back to an angle here. So that means in order for us to write our displacement vector, we have or cos omega ti plus or sine omega tj. And that is measured in m4 meters. So part 2 then says, derive an expression for v, the velocity of the car at any time t. So we have, from part 1, we have already worked out that we have or cos omega ti plus or sine omega tj. From our knowledge of distance, speed, time, and rates of change, we should know that velocity is the rate of change of displacement with respect to time. So what we're being asked to do is differentiate this vector with respect to time. Now, differentiating a vector is quite straightforward. We differentiate the I part and differentiate the j part. So we're differentiating cos, but it has omega t. So we're differentiating with respect to t. So omega is effectively a constant. It's like a 3 or a 5. So what we get is cos becomes minus sine. So we have a minus, or the omega, which is the constant, comes out in front, and that gives us minus or omega sine omega ti. I know this can be tricky because the lack of numbers, but think of your omega as the constant. And the reason it's a constant is, well, first of all, they told us it was a constant angular speed. But in terms of differentiation, we are differentiating s with respect to t. T is the thing that changes. Everything else will remain the same. So then here we get plus. Again, sine is going to go to cos, but it is, think of your chain rule, you differentiate as normal, multiply by the derivative of the inner function, that is our constant. So we get or omega cos omega tj, and that's meters per second. So that is our velocity v. So then it says, use a dot product calculation to show the car's velocity and displacement are always perpendicular to each other. So in order for these to be perpendicular, so if S is perpendicular to V, then the dot product of S and V should equal a 0. So let's get our two vectors here. So S was or cos omega ti plus or sine omega tj, and our v minus or omega sine omega ti plus or omega cos omega tj. And how our dot product works, so if we want to get the dot product, we multiply the I coefficients together. So that's cos omega t. Remember, this is also called scalar product, which means we do not put in the I. Omega t plus, it's really important, that's a plus, and then the j components together, or sine omega t plus or omega cos omega t. Now, tidying that up, it gets us minus or squared omega cos omega t sine omega t plus or squared omega. If we want this to be clear, let's write the cause first. It's multiplication. Multiplication is commutative, which means the order we multiply doesn't matter. So you can write a cause and then sine, or sine and then cos. It really doesn't matter. But writing it this way allows us to see that we have two identical pieces, but one is a minus and one is a plus. So they effectively give us a 0. So therefore, we now know that the displacement will always be perpendicular to the car's velocity. So part 4, show that the acceleration of the car is always directed towards O. So this one is probably the trickiest. So the first thing we need to understand is they're asking us about acceleration. So when we talk about rates of change, we have S for displacement, differentiate that gets V, differentiate that again, and we get A. So remember, we have these pieces. So what we want to get A is we're going to differentiate V with respect to T. So I'm going to just put my V here so we have it handy. It is minus or omega sine omega Ti plus or omega cos omega Tj. So we're going to differentiate each part. So we end up with sine differentiates to cos, so we end up with minus or, and then we get an omega squared, cos omega Ti. Cos differentiates to a minus sign, so we get minus or, another omega comes out, so omega squared, sine omega Tj. So that's our acceleration. Now, what we want to do is show that this is always directed towards O. So it's got to do with the sign. So think about what we knew to begin with. So displacement was always directed away from O. Think of how we worked with that. So what I'm going to do is I'm going to pull out that minus and the omega squared, and I'm going to leave everything else. And that's going to look somewhat familiar to us. And an or there, sine omega Tj. And what I've got now in my square bracket was actually our displacement S. So we get minus omega squared S. So S pointed away from O. Look at our diagram. Therefore, minus omega squared. The omega doesn't really make a difference. It's the minus. When we multiply that S by a minus, which is actually acceleration, points towards O. Minus means opposite direction. Opposite direction. So really be clear about what that minus means with our vectors. So this is the SEC sample higher level paper question 7. We're going to work with part AI. So from part A, they tell us a bungee jumper of mass 75 kg jumps from a height of 35 meters above water. The jumper is tied to an elastic rope of natural length 12 meters and an elastic constant of 100 newtons per meter. Derive an expression for the work done when a spring of elastic constant K Newton per meter is stretched by X meters. So here we have work done by a varying force. The information that they gave us after part A, that's going to be needed for a future part, but it's not needed for now. This is a very generic formula we're going to derive with a K and an X. So the first thing we're going to do is we're going to get our formula for work from the log tables. And that is the one where we have a varying force. So it is force, the integral of force with respect to S, which is displacement. We need to think about what that force is. For us, it's Hooke's law. So F is equal to minus Ks. So just something to be aware of here. Work is a scalar, which means it does not have direction. Force is a vector, which is why we have that negative for Hooke's law. It is restorative force, which means it's coming back to where it started. So when we put Hooke's law in for our work formula, we're not going to put the minus. We're not going to put the direction. There is no need to do that. So we're just going to integrate Ks with respect to S. We're moving it from a displacement of 0 to x. So I'm going to use limits of integration here. So that allows us to get ks, add 1 to our power, divide by our power, and we're going to evaluate that between 0 and x, which gives us k x squared over 2 minus k times 0 squared over 2, which gives us work is equal to kx squared over 2, and work is measured in joules. This question comes from the 2023 higher level paper. It is question 1 part B. A particle moving along a straight line has velocity v ds dt equal to 2t e to the power of minus t, where t is greater than or equal to 0. Part 1 asks us, using integration by parts or otherwise, derive an expression for s of t, the displacement of the particle at any time t, given that s0 equals 0. So basically they're asking us to solve that differential equation. So our first step is to write down our differential equation. So it's very, very clear because we have a little bit going on up there with a v. So we want to write it in the form ds dt. Now, we have ds dt. We want to separate to make sure that we have all of the same variables on each side. So on the left-hand side, I'm just going to stick with a ds. I'm going to leave everything else on the right-hand side. If you want to bring over that too, you can, but there is no need. We're going to integrate. So when t is 0, they've given us this little piece here. S is 0, and we want to get an expression for s in terms of t. So that left-hand side, very straightforward, is just going to integrate to an s. It's good to do that straight away because that is worth some marks. Now, the right-hand side, usually we would do our little checklist. How should we integrate? However, they told us very nicely here to use integration by parts. So we go to our log tables and we have our integration by parts formula. The only thing you need to remember when using this integration by parts formula is the order that things must appear. So we have IN, L, A, T, E. So inverse, L for logs, A for algebra, T for trigonometric, and E for exponential. So we have two bits here. We have the T or the 2T, which is algebraic. And then we have an exponential. So they're actually already in the right order. So when we're integrating this, so I'm going to just bring this all to the side so we can work with it. So we have the integral of, and I'm going to leave the limits just for a second. So 2t e to the power minus t dt. So in terms of our formula, we have u dv. So this is our u and this is our dv. We're happy with that order. So what we're told to do is to first of all have u, which we have, but get then v. We don't have v. So a good starting point is to take our u and differentiate that. So that is du dt, which gives us 2. So du is equal to 2 dt. And then take our dv, and that's equal to e to the minus 2 dt, and then we integrate both sides, which gives us v is equal to e to the power minus t. That doesn't change, but there is a little bit of chain rule there. We do have a formula on page 26 that will just give us this as our answer. No need to put in any plus c or anything like that because we're going to use our limits when we bring that back to the question. So we get v is equal to minus e to the power of minus t. So this becomes u, which is 2t, times v, which is minus e to the power of minus t, minus the integral. So just from our formula, that's u, v, minus our integral v du. So v minus e to the power minus t, and then du, which is 2 dt. And then that tidies up to minus 2t e to the power of minus t. We have minus minus and a 2, so we can actually bring that 2 out in front of the integral if that helps. And we're left with something like this. I put just a box around here. And then if we bring this down, we get equals minus 2t e to the power of minus t plus 2, and then this integrates to minus e to the power of minus t. So again, a little bit of our chain rule there. So if we bring this back, what we're left with is minus 2t e to the power of minus t minus 2 e to the power of minus t. And we're evaluating that between 0 and t. Be really, really careful in situations like this where we have a 0, we're subbing in. Subbing in a 0 does not necessarily lead to a 0. Just be very, very careful with that. So here we get s minus 0. So that is going to just disappear. Here we have minus 2t e to the power of minus t minus 2 e to the power of minus t minus. Now we sub in our 0. 2 minus 2, we put a 0 in here, e to the power of minus 0 minus 2 e to the power of minus 0. Now, because this first piece multiplied by 0, it's going to disappear. However, this bit here, e to the power of 0, is actually 1. So what we're left with is minus 2t e to the power of minus t minus 2e to the power of minus t minus minus, and we get a plus 2 there at the end, and that's our answer. So then part 2 here asks us to calculate s of 3. So what is s when we sub in 3 for t? So s of 3, so that's going to equal to minus 2 times 3 e to the power of minus 3 minus 2 e to the power of minus 3 plus 2. Just give ourselves a little bit of space and let me label this. So this is a nice little question. We're just going to go straight to our calculators and we're going to put that in, and I'm going to round it to 2 decimal places, so 1.60 meters. This question comes from the 2023 higher level paper, and it is question 4. A ball of mass mkg is projected with initial velocity 15 meters per second. I'm just going to highlight this because it's something we're going to need later in the question. It's projected with initial velocity 15 meters per second vertically downwards into a tank of water. The ball travels through the water against an upward buoyant force that is 4 times the magnitude of the weight of the ball and a drag force of mv squared newtons. Draw a diagram to show the forces acting on the ball while it is moving downwards through the water. Okay, so here's our ball, and one thing that will always act on any particle we have is weight. So we have our weight, which is mass times gravity. Now, we're told that there is an upward buoyant force. So that's not dependent on anything. So buoyant, we're going to use B, and it's 4 times the magnitude of weight, which is going to be 4 mg. So 4 times. Now, the direction we have is downwards in this question. So we're moving down, which means that the drag force is going to move up. So the drag will always go against the motion or against the direction of travel. So we get here our drag force, which we can call D, which is mv squared. Now notice how that initial velocity does not go on our force diagram because it's not a force. You can put it to the side if you like, but really that's just going to be needed later on in the question when we're setting up our differential equation. It's telling us what's initially happening for our velocity, so it is not relevant right now. So the next thing, part 2, what they ask us to do is show that while the ball is moving downwards, the rate of change of its velocity, v, with respect to its distance, s, so this is v dv ds, below the surface of the water, can be expressed by this differential equation. So v dv ds is just another way to say acceleration. So what we're going to start with, anytime we have a force diagram, we always start with F equals ma. We're moving in a downward direction, meaning mg will be positive. Then we take away anything that's moving upwards, so our buoyant force, and then our drag force, and that is equal to mass times acceleration. The m's can be divided out, giving us minus 3g minus v squared equals a. Now, we're very close to what we were given, so we actually can calculate minus 3 times g, which is minus 3 times 9.8, gives us minus 29.4 minus v squared. And then we know that actually acceleration, there's two ways to write it. We can write it as dv dt, which relates velocity to time. But in this case, they want us to relate velocity to displacement. So it's v dv ds. So we get v dv ds equals minus 29.4 minus v squared. And now we have our differential equation. Part 3, solve this differential equation to find an expression for v in terms of s. So it's very nice in this question that part 2 asked us to get the differential equation but gave us what that differential equation should be. So even if we weren't able to get the correct one, or even if we weren't able to do it at all, we still have the differential equation, so we can move on to part 3 to solve it. In the case where you can't work out the differential equation, or in the case where you've worked it out incorrectly, do use the one that they've given you, because if you use an incorrect one, it may not, you may not be able to integrate it. So our first step, once we have the differential equation, is to separate it. What we mean by that is we want to move our variables to each side. So here, what we're going to do, we're going to bring the whole 29.4 and the v squared across. You can do that with the negative. You can leave the negative on the other side. It doesn't really matter. So for us, what I'm going to do is I'm going to keep my v dv ds. I'm going to pull out that minus, and I'm going to bring that whole bracket underneath the line on the left hand side. So we have 29.4 plus v squared dv, and then I have a minus ds, and we're going to integrate both sides. Now, S is our displacement. So displacement, unless you're told otherwise, will always start at 0, because we talk about generally how far you've displaced from its starting point. So when displacement was 0, that was at the very start, the initial velocity, we had this earlier in the question, is going to be 15. And then when the displacement is s, the velocity is v. So on the right hand side, that's going to integrate really, really nicely and quickly. Generally, you're going to get marks integrating both sides. So don't be put off by kind of complicated integration. Make sure you do your simple integration, even if you can't do the left hand side, or if you feel that that's wrong, or if you give up. Still, we have a minus s on that right hand side. Our focus is going to be, so I'm going to just put that in. So that's my minus s, and we're going to evaluate that between 0 and s. Straight away, I've got some marks. Now over here, the left hand side, I'm going to just bring it over here so we have a little bit more space to work. So we have the integral evaluated between 15 and v, 29.4 plus v squared dv. So our focus now is, what do we do with this? So here's our little checklist. First thing we check is there a formula on page 26? Now we have 3 little exceptions that won't look exactly the same, but otherwise it has to be identical. That bottom line does look like something we may be able to use. However, the fact that there's a v in the top line is a little bit, we're not really sure It's not going to be exactly like something we see on page 26. The next thing is it a composite function? Now, this is a composite function. It can be really hard to see. Effectively, what we have is a 1 over x, but the bottom line has then been made more complicated. I know students really struggle with identifying this, but let me give you kind of how you could make sense of this in an exam. So if you weren't sure if it's a composite function, you could say, right, is it integration by parts? Now, the one key giveaway that this is definitely not integration by parts is the fact that the two parts, yes, we can make this a multiplication because integration by parts should be a product, should be multiplication. We can create that second piece as a bracket to the power of -1. However, what gives it away that it's definitely not integration by parts is the two pieces are both algebraic. So for our integration by parts, we'll see that the two bits will generally be different. So go back to our inlate, I-N-L-A-T-E, inverse, L for logs, A for algebra, T for trigonometric, and E for exponential. They should be two different pieces. So the fact that these are both algebra implies that it's probably not integration by parts. So that gives us back to our composite function. It is a good idea to really try and make sense of your composite function and try figure it out. If we have a composite function, we're going to use substitution. The substitution, we always sub in for the more complicated piece. So we use u, and I'm going to take the bottom line because that's more complicated than the top line. The top line is just a v. We're not going to go anywhere with that. So we get 29.4 plus v squared, and then we differentiate that, du dx, and that, du dv, and that gives us 2v. And then what we want to do is we want to rearrange this. So we get du is equal to 2phi dv. Now what we're effectively trying to do here is we want to replace this with the du. Now if you look at our question, we have a v dv. We don't actually have the 2. So what we can do is we bring that 2 back over the line as a half. So we have a half du is equal to v dv. And now we can sub that in for the bit in yellow, which means when we get to our integration by substitution, it's going to look something like this. So we have the integral and we have all over u because we've simplified it. And then we have a half du. So we have something that looks like this. Now that can be cleaned up into 1 over 2u du. Equally, you can pull that half out in front if you want, absolutely fine. And then when we do that integration, we end up with ln of 2u and then divided by the derivative of the inner function. So again, if you want to think that as a half in front, that's absolutely fine. So when we come back over here to that left-hand side, what we have is a half, the natural log of, instead of 2u, we're going to put back in what we had. So 2 and our u, which was here, make sure you do any substitution back in before you do your evaluating. And then that needs to be evaluated between v and 15. Now, if you pull the half out in front over here, you get a slightly different answer. So you will end up with a half natural log of u, and you might feel, well, that's completely different. However, because of the way we're going to work this through, because of how we evaluated, you will end up with the exact same answer if you pull that half out in front and you've just a half ln u for this part here. So now that we have our integration done, let's do our evaluating. We have a half natural log of 58.8 plus 2v squared. Take away a half natural log 58.8 plus 2, and instead of v we're putting in 15 squared, and that's all going to equal to minus s minus times 0, which effectively all just disappears. So we're left with minus s on this side. So I can pull that half out in front and then just focus on the natural logs. Subtracting our natural logs allows us to simplify using our laws of logs. So we have 58.8 plus 2v squared, 58.8 plus 450, and that's all equal to minus s. Let's get rid of the half. So we get natural log of 58.8 plus 2v squared all over 508.8, and that's going to equal minus 2s. Remember what we're trying to do, we're trying to find an expression for velocity, v. So we're going to take e to the power on both sides to get rid of that natural log, or however you do get rid of your natural logs. So yeah, 58.8 plus 2v squared. This point all we're doing is some algebra. So the differential part is really done. Minus 2s, we bring our 508 above the line. Really take care with this because this kind of stuff can go wrong so easily. So really pay attention. Make sure you are not rushing through it. You're not doing anything terribly silly. You don't make mistakes that'll dock you marks when you've done all the hard stuff. So 58.8, we're going to divide that by 2. So we get v squared equals, you can put it all over 2 or just divide across. I'm going to just divide it across to keep it nice and simple. Minus 29.4. So then v is equal to square root of 254.4 e to the power minus 2s minus 29.4, and that's meters per second. So part 4, the ball is at its maximum depth d when v equals 0. Calculate d. So the depth, we're really talking about s, its displacement. So what we're going to do is we're going to sub in when v equals 0, and we're going to try and find a value for s. So I have our answer from part 3 here on the board. V is equal to the square root of 254.4 e to the power of minus 2s minus 29.4. However, if we sub in v equals 0 here, we still have a substantial amount of work to do to get s on its own, to isolate it. So another option is, and this is a really good idea anytime you have a follow-on question from solving a differential equation, think about, is there a line in my previous answer that might be better, that might be, I suppose, easier for me to use than our final answer? So here, because we're looking to find a value for s, so the depth, is there a line from part 3 where we had s either isolated or nearly isolated? And the answer is yes. So we did have a line that looked like this. So minus s is equal to minus half the natural log of 58.8 plus 2v squared all over 58.8 plus 450. Now what that does is it allows us to get an answer for s much quicker. So it turns this sum. So all I'm going to do is I'm going to bring that minus across, and we have the natural log of 58.8 plus 2 times 0 squared. So that's just going to disappear. And then we have 508.8 down there at the bottom. So we can do a little bit of cleanup. And all we're doing now is going straight to our calculator. So this becomes a much nicer and easier sum. We're going to put this into our calculator and we get 1.08 meters, which is correct to 2 decimal places. Now it's absolutely fine to use your final answer and sub that in, but it is going to take away a little bit of time. Remember, the exam will be very tight for time, so anywhere you can save time, you want to do that. So this is a great little trick in these differential equation questions to speed yourself up. So we're told that after reaching its maximum depth, the ball changes direction and begins to move upwards through the water. Draw a diagram to show the forces acting on the ball while it's moving upwards through the water. So here's our ball, and again, it doesn't matter what way it's moving, weight will always move, or will always work in a downward direction. So weight is mass times gravity. Then we have an upward buoyant force, which they had already told us was always upwards. That's at the very start of the question, which is 4 times the magnitude of weight. So that doesn't change. That's 4 mg. Now we need to think about, well, what way are we moving? So we're moving upwards through the water, which means this time drag is going to move downwards. Drag always goes against motion. So think of it as a type of resistance. So then this is our drag, which is mv squared. So they want us then, once we have this part done, to write down a differential equation for the rate of change of velocity. It doesn't say with respect to displacement, so we're happy to think of this as just dv dt. And we're going to start with our F equals ma. We always start with the direction of motion, which is why that additional arrow is so important. So we have 4mg minus mg minus mv squared is equal to ma. And we get rid of all these m's. So we have 4g minus g, which is 3g minus v squared is equal to a. So we can rewrite that as dv dt. You can leave that as 3g, but we already know that that is 29.4. And that's minus v squared. So that's our differential equation for when the ball moves upwards through the water. So this question comes from the 2023 higher level paper. It's question 7, part B. A learning curve is a graphical representation of how a person's ability to perform a certain task increases with the time the person spends learning or practicing that task. A student wishes to be able to spell 2,000 difficult words. The rate of the student's learning may be modelled by this difference equation, which is dn dt is equal to k times 2,000 minus n, where n of t is the number of these words the student is able to spell after t hours of learning, and k is a positive constant. At the start of their learning, students will already be able to spell 250 of these words, i.e. n of 0 is equal to 250. When t equals 0, n equals 250. Solve the differential equation to find an expression for n in terms of k and t. So step 1, because we've been given the differential equation, is to separate it out so we have different variables on each side. So we're going to bring the n's to the left-hand side. So I'm going to bring this whole bracket across. So I get 1 over 2,000 minus n dn is equal to k dt. And we're going to integrate both sides. And when t is 0, we were told that n is equal to 250, and we were trying to find an expression for n in terms of t. We're not subbing in for our k. So the left-hand side is a version of a plus ax plus b, or some version of that we're integrating, which is a more complicated version of just 1 over x. So when we integrate that, we'll do 1 over x first, we get ln x. When we integrate 1 over ax plus b, we get ln ax plus b. But because it's more complicated, we're effectively using the chain rule in reverse. We have to divide by the derivative of the inner function. B is a constant, so it disappears. Ax just goes to a. So it's all over a, or another way to write that is 1 over a ln ax plus b. This is a really common one, so do watch out for it. So we have here on the left-hand side the natural log of 2,000 minus n. Be really, really careful here. You might think there's no coefficient of n, but there's actually a minus. So we're going to divide by a minus 1, which effectively just makes this negative. We're going to evaluate that between 250 and n. On the right-hand side, we get kt, which is between 0 and t. So then we get minus the natural log of 2,000 minus n minus the minus, which gives us plus natural log of 2,000 minus 250, and that equals 2 kt. So what we get, if you want to kind of pull that minus out in front, we can do kt equals minus, and then we can do the natural log of 2,000 minus n all over 2000 minus 250, which is 1750. That is exactly the same as the natural log of 1750 over 2000 minus n. So you're absolutely fine to do that whichever way you prefer. We're trying to find n, so I'm going to flip this. So the ln 2000 minus n all over 1750 is equal to minus kt. We're going to take e to a power on both sides, which is going to leave us 2000 minus n over 1750 is equal to e minus kt. And that's 2000 minus n is equal to 1750 e to the power minus kt. N is equal to 2000, watch your signs here, minus 1750 e to the power minus kt. So for part 2, we're told after 6 hours of learning, the student is able to spell 1500 of these words. Calculate k. So we have our formula here that we worked out from part 1. However, because we're looking for k, we can go back to part 1 and go through our workings and see, is there a line which will help us to isolate what we want? So in this case, k, rather than us having to put in the values and then work backwards. It's absolutely fine to put in the values and work backwards. So our values are when t equals 6, n equals 1500. But in order to work backwards, it's going to take a few steps. So going back to part 1, we can find the line that reads kt. Well, ours reads slightly backwards. So kt equals minus natural log 2000 minus n 2000 minus 250. And there's a minus in there at the front. So we can use that instead because that's going to be much, much easier for us to isolate our k. So to get k, it's going to be minus the natural log of 2000 minus 1500 all over 1750. We can do a little bit of cleanup on that, and then we're going to divide that whole thing by 6 very, very quickly. We end up with the natural log of 2 over, sorry. So we can tidy that. Actually, do you know what? I'm not even going to tidy it up. I'm going to go straight to my answer, which is 209 at 0.209. So lovely and quick. So part 3 asks us to sketch the shape of a graph of n against t to show the model's prediction for the student's learning curve. So there's a few different ways you can work that out. In your calculator, you can put in the formula and you can just change your t value from 0 to 5, 10, and so on. You can use the table function if you've a Casio or the function on other calculators. So I'm going to create a table just so you can see the values. So when t is 0, we get 250. You don't need to do this. However, it might be helpful for yourself to have these written down just rather than going straight to plotting. Once you have these, we're going to start plotting the points. So that's 0, 250. This is 5 and 1385-ish. This is 10 and 1784. This is 15 and 1924. This is 20 and 1973. And then we have 25 and 1991. And our final point is 1997 with our t equals 30. And we're going to do our sketch, which gives us a graph that looks like this. So this question is from the 2023 deferred higher level paper, and it's question 4. So it's quite wordy here. I'll let you read it, but we're given a differential equation, which is dp dt is equal to or p times 1 minus p over k, where or and k are constants. And then it tells us for a certain species of insect in an environment, we know that the population can increase up to 8% per week. So or is equal to 0.08. At t equals 0, there are 20 insects in the population. And it also tells us when the population p is small relative to k, the ratio p over k is also small. and the model can be approximated by the simplified differential equation dp over dt is equal to RP. So they want us to solve the simplified differential equation. So first thing we're going to do is we're going to separate that out. So I'm going to bring that P over and I'm going to leave the R where it is. We're going to integrate both sides. We're told when T is equal to 0, P is equal to 20. So that's T and that is P. So on the left hand side, this is going to give us ln P and we're going to evaluate that between 20 and P. And over on the right, we get RT between 0 and T. So I'm going to move up here with a bit of space. Get ln P minus ln 20 is equal to RT minus R times 0. R times 0 is nothing, so we can ignore that. The natural logs, we can bring those together using our laws of logs. And then we're going to take e to the power on both sides. That leaves us P over 20 is equal e to the power of RT. And P is equal to 20 e RT. And they told us here that R is 0.08. So we can put that in. E to the power 0.08 T. So that's our answer. Part 2 then asks us to calculate P to the nearest whole number when T is equal to 12. So we have our formula here from part 1. So that's 20 e to the power of 0.08 times 12. That can go straight into the calculator, and correct the nearest whole number is 52, and that's insects. So part 3, explain why this approximation is not practical for predicting the long-term behavior of the population of insects. So the issue here, it's twofold. So one of the first things is because we have an exponential. So if we go back to our formula, we have P is equal to 20 e to the power of 0.08 T. If we think of this as the limit as T goes to infinity of P, it's literally going to keep going and going and going. It's going to keep going to infinity. So it's going to get bigger and bigger and bigger. But the issue with that is we can only use this approximation when the population P is small relative to K and the ratio P over K is small, okay? That's when they told us that this approximation can be used. So our issue is that currently we have an unbounded population, which basically means it's going to keep growing. It has no limit in the sense it's going to keep getting bigger. And we then effectively don't have this scenario where P is small relative to K. So there will come a point where P gets so big that it becomes too big relative to K and we can no longer use that approximation. So for part 4 now, we're asked to solve the differential equation for Verhulst's model, which is more complicated than the one we previously had. So what we're seeing in this question is that idea of a modeling where we're going through iteration after iteration. So our first iteration was a little bit simplistic. It wasn't perfect. We talked about the reasons why. Now we've come to a slightly more accurate model, which hopefully, as we work through, we'll see, does it deal or does it fix some of the issues that we had with the previous model? So here we have dp over dt is equal to RP times 1 minus p over k, and we want to find an expression that relates p, k, and t. So we're solving to get p equals. Now, note that 1 over y times x minus y is equal to 1 over x times 1 over y plus 1 over x minus y. So this little piece of information is something we're going to use. And let me just put a box around it. And this is going to help us with our integration. So the first thing we're going to do is I'm going to just write my differential equation here. And we're going to separate this out. So I'm going to bring all of this to the other side and I'm going to leave my or. So that gives me 1 over p times 1 minus p over k, and that's dp is equal to or dt. We're going to integrate both sides here, again, same initial constraints. We know when t is 0, there were 20 insects. We're going to evaluate that to t and to p. So that piece on the left-hand side, we're just going to bring it to the side and use our little note and try figure out how to make this into something that's easier to integrate. So we know when we have 1 over y, which we could have as p, times x, so 1 minus the same as before. So we don't exactly have what's here yet. So notice that the thing in front of the bracket should be the same as the thing that comes second after the minus in the bracket. So what we're going to do with this is we're going to create a single fraction in the bracket. So we're going to do k minus p all over k. So we've done a common denominator, and that gives us k over k for the first fraction, and then we've simplified it. So then we have here a complex fraction, and when we divide by a fraction, it's the same thing as multiplying by its reciprocal. So that means I can think of this as 1 over, this p, think of that as p over 1, p times k minus p all over k. That's 1 divided by p times k minus p over k, which is the same as 1 multiplied by k over p, k minus p, which effectively gives us k over p bracket k minus p. Now, why is that important? Well, because, let me just draw a line under the integration piece. So what we have now in our fraction is k over p bracket k minus p. So that bottom line looks exactly like what we want. So if we pull that k out in front, I can now have exactly what that fraction is showing us. So that means, again, just keeping that k outside, this is effectively the y, the x minus y. We now can say that inside that square bracket, I get 1 over x, for this it's 1 over k, times 1 over y, which for us is p, plus 1 over x minus y. Now, that k in front and the 1 over k in front, well, just inside the bracket, they can multiply together. So we're left with 1 over p plus 1 over k minus p. And this is going to go in instead of this piece here. So there is quite a significant amount of algebra to do before we even get started with the integration. So now let's actually start that integration process. So we now have two terms on the left-hand side. So that gives us simply the natural log of p plus the natural log of k minus p. But this is a backwards version of the chain rule. So we need to divide by the derivative of the inner function. K is a constant. P is our variable. So that gives us a minus 1. If you want to kind of keep that neater, you can just throw your minus in here, save your fraction. So that's going to give us a nice fraction. So we're going to do RT 0t. So that gives us ln p over k minus p, which we're going to, let's see, can I make that a bit neater? So p divided by k minus p, and that's what we're going to evaluate between 20 and p. That gives us RT minus r times 0, which goes to 0. So we get the natural log of p over k minus p, and take away the natural log of 20 over k minus 20. And that is equal to RT. And this can in turn be simplified using our laws of logs as well. It's not as pretty. You can go straight to kind of the tidy up if you're more comfortable with fractions. However, what we're saying is we have the two fractions, the first one divided by the second. Instead of dividing by a fraction, what we do is we multiply instead by its reciprocal. So we end up with this. We're going to take e to the power on both sides. So we're left with p bracket k minus 20, 20 bracket k minus p, E lateral log is gone, and e to the power of RT. So that's pk minus 20p is equal to 20k minus, so actually I'm gonna, I'll put this in a bracket, e to the power of RT. We're trying to get p on its own, so we have a pk minus 20p is equal to 20k e to the power of RT minus 20p e to the power of RT. And if it's easier, we can write this as actually kp, just for alphabetical sake. So we're trying to get p on its own. So let's get all of our p's over to one side. So we have 2 of them here already. I'm going to bring over that 20p e to the power of RT. That's 20k e to the power of RT. We want to pull out our p, and then we're left with an a 20 e to the power of RT, a minus 20, and then a plus k. And then final step, to get p on its own, we get 20k e to the power of RT divided by 20 e to the power of RT minus 20 plus k, which is our differential equation solved. So part 5 tells us p is equal to 39 insects when t is equal to 12 weeks. Calculate the value of k to the nearest whole number. So we have our answer here for p, and we can use this straight away with p equals 39 and t equals 12. However, we can go back to a previous step in part 4 to see is there an easier place where we might have k isolated, or it might be easier to work. Now, this particular question, we don't have k isolated. However, we might be slightly easier to work with this line. So what I'm going to do is I'm going to bring the 2 k's over together. I tend to prefer to manipulate in algebra rather than start our substitution in too early, but it's completely up to you. I'm going to pull out my k, 20k e, sorry, that k is gone, 20 e to the power of 0.08t, and that equals 20p minus 20p e 0.08t. So we get k equals 20p minus 20p e 0.08t divided by p minus 20e 0.08t, and then we can do our substitution. So that's k is equal to 20. Instead of p, we're putting in 39 minus 20 times 39 e 0.08 times 12 all over p, which is 39 minus 20 e to the power of 0.08 times 12. And we go to our calculator for this, and we get 94.99, which to the nearest whole number is 95. And then part 6 asks us to explain the significance of k in this model. So in this model, what that k represents is that upper limit. So as the population increases, it will start to steady out at 95, which is why that this is much better for us to use for very large populations compared to the approximation that we had earlier in the question. This question is from the 2023 Deferred Higher Level paper, and it is question 5. So for part 3, we are first of all told that a more sophisticated model for the motion of a ball that is thrown vertically upwards includes the effect of air resistance. The rate of change of velocity of the ball in terms of time t during the upward part of the journey can be modeled by the following differential equation. dv over dt is equal to minus g minus kv. So remember, dv dt, we're talking about acceleration. Where k is greater than 0 is a constant. Take the initial upwards velocity of the ball to be 20 meters per second. Solve this differential equation and find an expression for v in terms of t and k. So effectively what we're seeing here, if we think in terms of our F equals MA, we had two things that were working downwards. We would have had weight, which was mg, and then we would have something that would have been air resistance, which would be an mkv in some form, and that would equal to a mass times acceleration. And then the masses would have been divided out, which would have left us with this acceleration formula. So we've seen kind of building this in other questions. So that is where that equation came from. And that's going to be relevant later on in the question when we're asked to work with it. For now, all we care about is we have the equation and we want to solve it. So first thing we do is we're going to separate out our variables onto different sides. I like to leave my minus on the right hand side where I can. Just remember, you can't split out that k. A lot of practice needs to go into splitting and separating out these differential equations. It must be either a multiplication or division. You should never add or subtract to move things to the other side. And the reason for that is because there should be a multiplication by that dv or by that dt. So what we get over here is 1 over g plus kv dv equals minus dt. And we're going to integrate both of these. We're told that the initial upwards velocity is 20. So when t is 0, we have velocity of 20. And we're trying to figure out when the time is t, what will be an expression for v. So that right-hand side is very straightforward. It's going to be minus t. So I like to leave my minus on that side, but it's absolutely fine to bring it to the left if you want. Notice how the left-hand side here is in the form of 1 over ax plus b, which is effectively a version of the integral of 1 over x. So that gives us the natural log, but we need to deal with the fact it's not just going to be natural log of x. So this one here will be natural log of x, while this one here will be the natural log of ax plus b, but then we divide by the derivative of the inner function, so we divide by an a, or put it as 1 over a. So bear that in mind. We see this a huge amount. Be very, very familiar with it. So this becomes the natural log of g plus kv. Remember that both g and k are constants. So when we differentiate g plus kv, we're left with just k. So that can be written as 1 over k, or we divide the whole thing by k, whichever you prefer. And we're going to evaluate that between 20 and v. Now, just clearing the screen so we have a bit more space to work, we get 1 over k natural log g plus kv minus 1 over k natural log g plus 20k. That's going to equal minus t minus a minus 0 like that, but that's effectively going to just disappear. So we can pull out the 1 over k in front, and then we're left with 2 natural logs subtracted. So for the natural log subtracting, we can use the idea of our laws of logs. And taking 2 logs away, we can instead write that as the so as a fraction g plus kv over g plus 20k. I like to write this single log because as soon as you have a log equation, you're trying to get one single log on its own, so you can then convert it. So that gives us minus t. Bring that k across, g plus kv all over g plus 20k, and that becomes minus kt. Now we can take e to the power on both sides. So that gives us g plus kv, g plus 20k, and that is e to the power minus kt. Remember what we're trying to do here? We're trying to get an expression for v, so we're going to do g plus 20k e minus kt, and then we have kv equals g plus 20k e to the power minus kt minus g, and then v we're going to divide across by k. And that's our answer for v. So part 3 asks us, using k equals 0.1225, calculate the time the ball takes to reach its maximum height. So we do need to understand what maximum height means. So maximum height is where it will stop. So it is going to have v equals 0 at that point. So we can take our formula that we had as our answer to part 2. However, if we sub in v equals 0 here and we try to then rearrange to get t, it's going to be a bit of a pain. So if we look back to part 2 and find a line where t is either isolated or nearly isolated, it's going to make our lives so much easier for this question. It's going to save us time. There will be less steps. Less steps means it's less chance of us making a mistake. We want to create something where we can just go straight to our calculator. So I'm going to go back to the line that looks like minus t equals 1 over k, a natural log g plus kv over g plus 20k. That is nearly got a t isolated. So what we're going to do then is simply change the sign. So t equals minus 1 over k, so that's 0.1225, natural log of g, which is 9.8, plus k, 0.1225, times our velocity, which is 0, all over g, sorry, I'll put in 9.8 plus 20 times 0.1225. We're putting this in the calculator. That bit's going to disappear, so I'm not even going to put that bit into the calculator. We can go straight to our calculator and it's going to give us our time straight out. No rearranging or solving required. This is a simple calculation. Now, you've already done the hard work. You've already gone from t to v. So to go from v back to t, you're kind of undoing or redoing the work you've done in the previous part. So in these kind of questions, when we have a differential equation and then they ask us to do something as a follow-on, really focus on, could I do this in an easier way? Is there something in my previous step where I have isolated or nearly isolated the variable that I want? So in this case, is there a line where t is nearly on its own? And the answer is yes. And that's the one you want to use. That will speed you up. Remember, these exams, you can be really, really tight for time. So anywhere you can save a bit of time is great. If you're doing these for practice, yeah, absolutely, it's great practice to sub in your v equals 0 and rearrange, but that is algebra. It's not going to be our differential equation. We want to focus on the things that are specific to applied maths, the pieces that are going to get us a lot of marks. So part 4, write down a differential equation for the rate of change of the velocity of the ball on the downward part of its journey. So the first thing we're going to do is we're going to look at the force involved. So here is the ball and we have, of course, weight working down, which is mass times gravity. Bear in mind what direction we're moving. So this is on the downwards part of its journey. So our acceleration is down this way, which means that any air resistance is going to be coming back this way. So this resistance, based on what we've seen before, is mass kV, which means if we think about this in terms of our force, F equals ma, it's going in the downward direction. So we have mg going down minus mkv is equal to mass times acceleration. The masses then disappear and we get something very similar to what we had before. The signs of the sign of gravity is going to be in a positive in this case. So we get, for our differential equation for the rate of change of velocity, so that's dv dt, is equal to g minus kv. So this question comes from the 2023 deferred higher level paper and it's question 7, part 3. After the collision Q experiences a restoring force F, which is proportional to x, the displacement of Q from its initial position, where K is the constant of proportionality. That is, the restoring force may be modelled as being equivalent to the restoring force exerted on a particle by a spring of spring constant K stretched through a displacement x. So that's something we are a lot more familiar with. Derive an expression for the work done when Q moves through displacement x. So First thing we want to look at is our formulas for work done. Given this is like Hooke's law, that we have that idea, the same thing as a string being stretched, we have work done by a varying force, and that force is going to be equivalent to the Hooke's law force. So we're going to start with the work is equal to the integral of force integrated with respect to displacement, but the force, we can write that as Ks. Now, the reason we don't use a minus is because work is a scalar while force is a vector. So we don't care about the direction of the force. That's all that minus means, that it is a restoring force. So what we're going to do then here is we're going to integrate this, and it is going to be stretched through displacement x. So it goes 0 to x. So we get W is equal to Ks squared all over 2, and we evaluate that between 0 and x. So that is Kx squared over 2 minus K times 0 squared over 2. So work is equal to a half Kx squared, and that is measured in joules. So this question is from the 2024 higher level paper, and it's question 3, part A. Particle moving along a straight line has acceleration a dv dt equal to t squared sine 2t, where t is greater than or equal to 0 and v equals 0 when t equals 0. Using integration by parts or otherwise, calculate v when t is equal to pi over 2. So this is a really good reminder that anytime we're working with integration or differentiation, any calculus, our angles must be in radians. So I go through that in more detail in our video where we look at the basics of integration, which is linked in the description below. So this question has very nicely told us that we're going to be using integration by parts, so we don't have to worry too much about the identifying. So our first step here is to write down our differential equation, which is dv dt is equal to t squared sine 2t, and then we separate it. So we can see that everything on the right hand side has a t, so nothing is coming over. We're just going to bring that dt over to the right hand side. So it looks like this, and then we're going to integrate. Our limits of integration, we're told that when t equals 0, v equals 0. So when t is 0, v equals 0, and that gives us, then we want to calculate v when t is, I'm going to go straight to pi over 2. That's going to make our lives so much easier. You are welcome to go to t and then sub in your pi over 2. It's completely up to you. So we're doing integration by parts. So here is our formula, and we need to remember when we're doing integration by parts, inlate, which means the order that we have for our parts must be inverse, then log, then algebra, then trigonometry, then exponential. So we have two pieces here. We have t squared, which is algebraic, and then we have sine 2t, which is trigonometry. So these are currently in the correct order. So I'm going to bring these over. I'm going to leave my limits in the main question just for a second. 2t dt. This is the integral of u dv. This is my u. This is my dv. So we have u equals t squared. So we differentiate that. Du dt is equal to 2t. So du is equal to 2t dt. And then we have dv is equal to sine 2t dt, and we're going to integrate both of these, which gives us v equals. So when we integrate our sine 2t, we're going to get minus cos 2t divided by 2. So just be really careful that you're looking at page 26, which is integration, because integration and differentiation of our trigonometric are very similar. Don't rely, maybe in an exam, don't rely on your memory for this. Really do double check, and remember that we have the basic chain rule here because it's a 2t, not just a t, so we're going to divide by that derivative of the inner function. So then in order for us to get an answer, we have uv minus the integral of v du. So that's going to be for us u, which is t squared. Move this down a bit. T squared times v, which is minus cos 2t all over 2 minus the integral of v minus cos 2t over 2, and du is 2t dt. So there is a 2 on the top and a 2 on the bottom here. That's very nice. So this little bit turns into minus t squared cos 2t all over 2. That bit's fine. Minus minus, I can pull that minus out. It gives me a plus, and this gives me a t cos 2t dt. Now, here's the thing. This little piece here requires integration by parts again. So we need to go and do our integration by parts. So what I'm going to do, so we don't lose anything, is I'm going to go back to my main question and I'm going to integrate the left-hand side, which is v, and evaluate between 0 and v. And then here on the right, we get minus, and this is all going to be in a big box because it'll all need to be evaluated in the end, t squared cos 2t all over 2 plus the integral of t cos 2t dt, and when we do all that, it's going to be evaluated between 0 and pi over 2. So I'm just going to clear the screen so we have a bit more space, and we're going to do integration by parts again. This is a common occurrence when we have sometimes when we have exponentials and trigonometric functions, they can actually get caught in a circular loop. We look at how to deal with that in the basics of integration video. Here, just a second time using integration by parts, and we will have our answer. So we have just a bit more space to work. So the left-hand side is going to be v minus 0, which is just v. We still have that minus t squared cos 2t over 2. And I'm going to look at that second part of the right-hand side. So this bit here, and that is going to need integration by parts again. So let's look at inlate. We have a t, which is algebraic, and we have a cos 2t, which is trigonometric. So we are in the right order. So let's take a look at t cos 2t dt. This is the integral of u dv. U is my t. My dv then, I don't really have enough space to draw an arrow, but we'll just underline the whole thing. That is our dv. So we have u is equal to t, meaning du dt is equal to 1. So du equals dt. And then we have dv equals cos 2t dt. We're going to integrate both sides. So v is equal to, cos becomes sine, and that's 2t, and we're dividing it by 2 again. It's that version of the chain rule. So then when we are doing our integration by parts, we have uv minus the integral of v du, which is going to be u, which is t, times v sine 2t over 2 minus the integral of v sine 2t over 2 du, which is dt. So this gives us t sine 2t over 2. And I'm going to pull that half out in front just to make that integration a little bit easier. So it's sine 2t dt, which is t sine 2t over 2 minus a half. Sine is going to go to minus cos 2t over 2. So when I put that back in, I get a plus t sine 2t over 2. Minus by minus is a plus, and then we have a half. So we have a 2 and a 2 on the bottom line. So we're going to have cos 2t over 4. So that's our full integral before we start evaluating it. So like I said, you can go between 0 and t. I'm going to go straight to pi over 2 because that's the answer that we want. And you're also welcome to use the idea of the constant of integration and do substitution. I think the limits method is a lot more efficient and it's less prone to error and it is a few less steps. So let's work what we have. So minus pi over 2 squared cos of 2 times pi over 2, which is just pi. You're welcome to put that in as 2 times pi over 2, but just to save typing when we get to the calculator stage, and just to save writing as well, I'm just going to put that in as pi for each of them, cos pi over 4, and then we're going to subtract minus 0 squared cos 0 over 2 plus 0 sine 0 over 2. So, and then we have cos 0 over 4. Be so careful. Subbing in a 0 does not always get us a 0. Here, that disappears because we're multiplying by a 0. However, the cos of 0 is 1, so we get a quarter there. So what we end up with here, if we start evaluating it, so minus pi over 2 squared cos pi over 2, that gives us pi squared over 8. Cos of pi is minus 1. And then we have pi over 2 sine of pi. Sine of pi is actually 0, so this whole thing ends up giving us a 0. Plus cos pi over 4, which is minus a quarter. I'll actually go straight to just minus a quarter. And then we have minus, and then 0, 0, and that's plus a quarter. So what we end up with is pi squared over 8 minus a quarter, which is minus 2 quarters or minus a half. And it's fine to leave your answer like that. Or if you want to change that to decimal, correct 3 decimal places, we get 0.73. This question is from the 2024 higher level paper and it's question 4. A snowboarder of mass m is traveling with the velocity v1 when he enters circular arc AB at point A. And we can see that in the diagram on the right. AB has radius 6.7 meters and center C. A, B and C lie in a vertical plane. And AC is vertical, BC is horizontal. A student models the motion of the snowboarder, ignoring the effects of friction and air resistance. At point B, the snowboarder leaves the arc and moves vertically upwards through the air. The student wishes to calculate V, the velocity of the snowboarder, t seconds after he leaves the arc. The force due to air resistance is now modelled as mkV. Part 4 asks us to draw a diagram to show the forces acting on the snowboarder while he's moving upwards through the air. So here is our snowboarder, and the first thing we're going to put in is weight, and we know how that acts and we know how that works. So that is mass times gravity. Now, for air resistance, we need to think about how he is moving. So he is moving upwards, which means the drag or that air resistance is going to work in the opposite direction. So that is mkV working down. There is absolutely nothing pushing him up. He does have an initial velocity. That's why he's moving up, but he will be decelerating that whole time. So then part 5 asks us to show that while the snowboarder is moving upwards through the air, so this scenario we've just drawn out, the rate of change of V with respect to t can be expressed by the differential equation dV dt is equal to minus G plus kV. Now, we know anytime you have a force diagram, we are working with F equals ma. So our force will always go in the direction that we are moving. So there's nothing pushing us in that movement direction, meaning we have a minus weight and a minus air resistance, and that is equal to ma. The mass it can be divided across, and we're left with acceleration is equal to minus, I can pull that out in front, g plus kv. And then the only thing we've left to do is replace our acceleration with the rate of change of velocity. So that gives us dv dt, which is another way to say a, is minus g plus kv. So part 6 then says solve the differential equation to find an expression for v in terms of t, k and v1. That's really, really important. That v1, it's so important. It is a little tricky part that was thrown in and was easily missed. So we're talking about the snowboarder moving through the air. It went into the air with the velocity that it had at point B. And it's important to remember that at point B, the initial velocity was actually v2. So I'm going to just make a little note of this. So easy to miss in an exam. So velocity at B was v2. So that's our initial velocity. A lot of students went straight to putting in v1 because that's what it asked for. However, in part 3, we were able to write v2 in terms of v1, and we're going to use that fact. But it's important that we really think in terms of our limits, that we have an initial velocity at point B. That's where it starts moving through the air. That is v2. So we have dv over dt is equal to minus g plus kv. This is something we've actually seen in a few questions. And we are going to leave the minus on the right hand side and bring everything else across. Remember, when you're separating these out, you really want to focus on division and multiplication. We should never have any adding or subtracting. And the reason for that is it needs to be multiplied by that dv or that dt. If it's added to it, it makes no sense. It cannot be integrated. So when the time is 0, our velocity is v2. And that's really, really important. That's what we're looking for. So then we have time and velocity v. So the right hand side, very straightforward, minus t, and we're evaluating that between 0 and t. The right hand side is something in the form of a plus bx, which is just a version of 1 over x. Remember, if we have 1 over x, it's going to integrate to ln x. If we have something a little bit more complicated, remember the ways to look out for this, there's always be a constant on top. It doesn't have to be 1, and it'll always be a little linear function underneath. So it'll be to the power of 1. In this case, it'll be a v to the power of 1, which is what we have. This is ln a plus bx, but because it is a version of the chain rule going backwards, we have to divide by the derivative of the inner function. So we're going to divide that by b, which means this left-hand side becomes 1 over k ln g plus kv. You can write that as a full fraction, or you can pull that out in front like we have, whichever way works. Okay, so now what we have is we have 1 over k natural log g plus kv minus 1 over k natural log g plus kv2 equals minus t minus a minus 0, which is just going to be 0. Now, focus on what we want. We want to find an expression for v. So just v, not v2 or v1. We'll plug that in a minute, but we want to get v on its own. So first thing I'm going to do is I'm going to pull out that 1 over k in front, and then I'm going to use my laws of logs to bring these two together. I get g plus kv all over g plus kv2. And that's equal to minus t. I then going to bring that k over g plus kv over g plus kv2 equals minus kt. Now just a bit more space to finish this off. We're going to get rid of that natural log. Let's do e to the power on both sides. And we get g plus kv over g plus kv2 is equal to e minus kt. Let's bring over that bottom line. So that's g plus kv2 e to the power of minus kt. Kv is equal to g plus kv2 e to the power minus kt, take away that g, and final step is then we're dividing by k. And we're nearly finished. So all we need to do now is answer the question, which is asking us for this in terms of not V2, but instead V1. So we're going to plug in what we have here. So that's G plus K times square root of V1 squared minus 13.4 G e to the power minus KT minus G all over K. And given its velocity, that is meters per second. This question comes from the 2024 higher level paper and it's question 6 part B. The acceleration of a particle moving in a straight line may be expressed in terms of its velocity v in meters per second and its displacement s in meters by the differential equation v dv ds, which we know is another way to say acceleration, is equal to e to the power of v squared over 4. Solve the differential equation to find an expression for v in terms of s, given that v equals 0 when s equals 0. So first thing we're going to do is we're going to separate this out. There's quite a lot going on here. So I have my v. I'm going to bring over my e to a power of v as well. Bring this down a bit. And that's going to be with respect to v. And then I'm just going to have my ds on the other side. If you want, you can write that as e to the power of a negative v squared over 4. If you're not a particular fan of your fractions, that's fine. And we can have our ds here as well. They told us that v is equal to 0 when s equals 0, and we're working to v and s. Now, the right-hand side, this is very straightforward. We are getting s and evaluating it between 0 and s. The left-hand side is a little bit trickier. So we do have a v and an e to the power of v squared over 4. So go to our checklist. Is there a formula on page 26? So there's nothing on page 26 that looks like this. Is it a composite function? And in this case, yeah, it is a composite function. So we are talking about integration using substitution. Now, integration by parts, you might say, oh, could I use integration by parts? It is possible. Well, it can be done. Do you have the time or the math skills to do it? That is a different question. How you need to be able to identify this is the fact that we have an e to the power of v squared over 4. And that is usually something like an e to the power of x. And if you think of it in terms of a composite function, imagine we have f of x is e to the power of x, and we have g of x is equal to minus x squared over 4. This could be written as f after g of x. So we put g of x into f of x, which is what gives us this. That's what we mean by a composite function. So this part here is a composite function. Don't worry about the other v. So for us to kind of think about it, I'll leave this here so you can kind of get a sense of it in terms of x. So we're working with the v. So what we have is we have something that's quite hard to work with. So I'm going to use this as a negative because of the way I've worked with it. If you had it underneath the line and it's positive, that's absolutely fine. This is called u substitution as well. So we're going to sub in a minus v squared over 4 as we're going to sub in u for minus v squared over 4, which makes that so much simpler. So what that's going to become is an e to the power of u rather than e to the power minus v squared over 4. But that's not everything, because we also need to deal with the fact that we have a dv. So because we have a dv, we need to differentiate this u to make a du dv and then split that out. So whenever you have your u, you then differentiate. So we bring down our power, take one away from our power, we are differentiating here. So that gives us du is equal to, it's minus a half v dv. Now, we have, I'm going to actually use a highlighter here, it might be easier to see. We want to replace a dv But we also have a v here we want to replace. Now we have that here, but that minus a half is not helping. So what we're going to do is we're going to bring that to the other side. So I'll go back to my purple. So minus 2 du is equal to v dv. So we're going to change this v dv that we've highlighted into a minus 2 du. So what that becomes is, for a nice simple little integration, is e to the power of u minus 2 du, which is integrate minus 2e to the power of u du, which, very straightforward, is just going to give us the exact same thing. So minus 2e to the power of u. So e to the power of u is going to stay exactly the same. The minus 2 is just a coefficient. It's not going to do anything. So when we plug this back in over here, we're going to change our u back to what we defined it as. So we get minus 2e to the power of minus v squared over 4. And we're going to evaluate this between 0 and v. So what we get is minus 2e to the power of minus v squared over 4 minus 2e to the power of minus 0 squared over 4 is equal to s minus 0. So that's gone. Just be careful. This piece here does not disappear because we have an e to the power of 0, which is actually 1, which gives us a minus 2. So just to give us a little bit more space to work, we get minus 2e to the power of minus v squared over 4, minus a plus, and that gives us a 2. Remember, this whole piece here is equal to 1, and that equals to s. What we're looking for is v in terms of s. So we need to get v on its own. So we get minus 2e to the power of minus v squared over 4 is s minus 2. Let's divide by that minus 2. Don't particularly like having a negative on the bottom, so I'm going to flip this to be 2 minus s all over 2. So you can think of this whatever way you want. If you divide by that negative first, so that flips the signs on the right hand side before you divide by 2. Whatever works for you. So then we take the natural log of both sides to get rid of that e. So we're left with minus v squared over 4 is equal to the natural log of 2 minus s over 2. Bring that 4 over. And then we need to bring over that negative as well. So v squared is negative 4 natural log 2 minus s over 2. Now, don't get freaked out about that minus, because we're going to square root it, and then you think, oh, can I square root a negative? But that minus, that natural log will actually be negative. So that minus is needed to undo the negative of that natural log. So if you prefer, you can leave it like this. If you prefer, you can bring this negative as a power. So that's going to be like a power of negative 1, which effectively, if you have a fraction to the power of negative 1, so imagine you have like x over y and it's the power minus 1, it effectively gives you the reciprocal. It flips it. Okay, so we're going to use that fact here. So v squared is equal to 4 natural log. This then flips, so 2 over 2 minus s. So all it does is flip the fraction. It's the reciprocal. And then we're going to square root that. And I can pull that 4 out in front because the square root of 4 is 2. We can do that because it's multiplying. And we get 2 over 2 minus s. And that's velocity, so it's meters per second. It will be absolutely fine if at this point you went straight. So here, if you went v equals square root of negative 4 natural log 2 minus s all over 2. And left it like that, absolutely fine. No problem at all. I just prefer that cleanup. I don't like the look of the negative underneath, but it's absolutely fine to leave it there. So part 2 says calculate the velocity of the particle when s is equal to 0.3 meters. So our answer for part 1 we have here in red, and we can plug our s straight in and then go to our calculator. So we don't need to go and find an earlier line in our previous calculation. We can use our answer. It's going to be very, very straightforward. We get 2 over 2 minus 0.3. Put that into our calculator and correct 2 decimal places, we get 0.81 meters per second. It's really important for questions like these that even if you think you have the wrong answer, or if you feel like you didn't even get it finished, plug that s equals 0.3 into whatever you have, because it is possible to get an answer for v even if you're incorrect in the previous part and get full marks. Equally, if you don't have a final answer v equals, you have something as s equals in the previous part, and again you still sub it in and you get an answer, you're still able to get full marks. At the very least, by subbing in an s equals 0.3 meters into something from your part 1, you will get a 10 marks. This question is from the 2024 higher level paper, and it's question 10b. This question was tricky because it didn't give us the differential equation. It was required of students to create the differential equation, which proved problematic. So let's work through it. A tank of uniform cross-sectional area contains water of height x meters. Water leaves the tank through a pipe at its base. The rate at which the height of the water decreases is proportional to x. So as a student, what you need to be able to do is take a sentence like this and convert it into mathematics. So the rate, unless they tell us otherwise, that's going to be d something dt, and that's true for maths as well. So the rate at which the height of the water. Now here's what's important. It told us the height is x meters. Okay, so the height is x. There is a h in the question, but they're telling us the variable they're using for height is x. And it decreases proportional to x. So it is proportional to a decrease, which means minus and x. So this idea of proportional, we've got a proportional symbol, decreases is minus, if it's increase, it will be a plus. I'll just put a circle around that so it looks clearer. One main issue, a lot of students put in dt was proportional to minus x, which caused a problem. So just be really, really careful. So the second thing that we need to do in order to make this a differential equation is get rid of that proportional sign. So proportional, all we're going to do is put in an equals and then a constant. So we're going to have a minus k x like that. That's enough to put in our equals. So proportional means as one goes up, the other goes up or down, as in this case. So putting a k, a constant in front of it as a coefficient will create that equation. So now that we've done that, we're going to separate our differential equation and solve it. So I'm going to bring the x over, but I'm going to leave the minus on the right hand side. I prefer to leave my minuses on the right if I can, because generally they're going to be easier to work with. So then we have when the time is 0, x is h. Now, it's completely up to you how you want to do this. Some students will go and work out, let's find an equation or an expression with x and t. I'll go straight to when t is 45, x is h over 3, and this will effectively get us a value for k. So integrating that left-hand side, that gives us the natural log of x, which we evaluate between h over 3 and h, and then we get minus kt, which is evaluated between 0 and 45. So that is the natural log of h over 3 minus the natural log of h is equal to minus k times 45 minus the minus k times 0. So I'm going to just ignore that part. So this is the natural log of, using our laws of logs, h over 3 divided by h. So that's natural log of a third, which is minus k over 45. Sorry, minus 45 times k. Now, If we get rid of this minus by bringing it over, so if I put the minus here instead, then I can bring this as a power. Think of your rules of logs. So the coefficient becomes a power, so it's 1/3 to the power of -1. So that's the same as the natural log of 3 is equal to 45k, which gives us k is equal to the natural log of 3 divided by 45, which is kind of nicer than putting in a specific decimal, but if you want to put a decimal, that's absolutely fine. It works out as 0.0244136. Now that we've got a value of k, we're basically going back and doing the same question, but we have different limits. Now, like I said, it's absolutely fine if you want to work out an expression for x and then sub in and get your k and then sub in again. And this is, sorry, minus k over, and that is dt. So we know when t is 0, x is h, and we want to find the time when x is h over 8. Now, here's the good news. I've already done a lot of the hard work. So I know this becomes ln, and it becomes the top number divided by the bottom number. So I get the natural log of what is effectively h over 8 divided by h, which is 1/8. That speeds me up a lot. Here, this is just a constant, so nothing's happening to it except we put a t there. And now what we have is same as before, natural log of 8, which gets rid of that. And then I'm going to divide that by 45. Sorry, divide that by natural log of 3 over 45. And that will give us our value for t. I personally don't like writing a lot of decimals. If you want to change any of these to decimals, you can. That's absolutely fine. But this works out as 85.2 seconds. So not a bad question. I think the setup really was what limited a lot of students. Thank you for watching. Hopefully you found this video useful. If you did, please like and subscribe. If there are any videos that you would like to see that aren't already on my channel, feel free to leave a comment below, and I'll either direct you to the video if it is there, or I will put it on the list to be recorded.